think I might have a problem. What the heck?
Togon.
Hello, and welcome to the next video on my channel. This is going to be a bit of a departure from what I usually do. I've been focusing mostly on high school mathematics for a little while, going through trigonometry. But I decided that I wanted to do a response video to one of my favorite mathematics YouTube channels, Dr. Peyam, who does a great job. Congratulations on 25,000 subscribers. You are fantastic. You deserve every one. He recently did a video on something called multiplicative calculus or product calculus. It's essentially like a multiplicative analog to regular derivatives and regular integrals. So I thought, I've never heard of this before, and I really love calculus. I've taken every calc class up through complex analysis, so I thought, well, this is something new. I'm always looking for something new to learn, and I thought it was really interesting. So I'm going to do a bit of an exploration, a bit of a study in this, see what I can garner from kind of looking at it from a differential equations kind of perspective, and I hope that you find this interesting, whoever's watching. So if any of my regular viewers have no idea what's going on, if any 5 of you have no idea of what's going on, just understand this is not supposed to be a continuation of any lessons I've done already. This is just a response to somebody else's video. So I hope you enjoy it, and if you watch this, Dr. Peyam, thank you very much for the fantastic videos that you make. And again, congratulations on
27,000
subscribers. So this video is going to be an exploration of something that I believe is called multiplicative calculus, and it involves things called product derivatives and product integrals. So before I define, or at least review what the definitions are for those two things, let's quickly recall, for those who know, what the definition of the derivative is. The derivative of a function, f of x, if you ask what the derivative of a function is, then it's defined to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Now you may think, well, h is going to 0 and you're going to divide by 0, so that's clearly a problem. But since h is going to 0 here, we're going to end up with f of x minus f of x, which is also 0. So we get 0 divided by 0 as sort of part of the definition of the derivative in calculus. So 0 divided by 0 is a much more tractable situation than non-zero divided by 0, only because a non-zero number divided by 0 is completely intractable. There's no information to be garnered from that in the context of regular old mathematics. But this is perfectly well defined, it works for most functions, and it's a lovely little thing. And similarly, the inverse function to this, or the inverse operation to this, is called the antiderivative, or integral, depending on your persuasion or what exactly you're trying to find, and it's usually written capital F of x is such that the derivative of capital F is little f, then we say that the antiderivative, or the sum over all the values multiplied by an increasingly tiny little interval of this function, little f of x, is equal to capital F of x plus some constant. Right? Okay, so if you're one of like a high school viewer and you haven't done calculus yet, and you don't understand what I'm saying here, it's totally fine. You don't need to worry about it if you're not sure what's going on. But these are essentially additive, right? We're subtracting and we're dividing. We are summing over all of these values that are being multiplied together. But this is regular calculus. We want multiplicative calculus, as in products, and powers, products and powers, not subtraction and division and sums and all that. We want products and powers. So let's erase this and let's get talking about, oh, there's gravity again. And let's get talking about the product versions of these things. So the product derivative, I've never seen this notation before, but I'm just doing it because it's the first thing that I thought of. The product, I'm going to say that the symbol for the product derivative of a function is lowercase p of some function f, and analogously the multiplicative or product integral of a function will just be capital P of f. I think that makes the most sense if I'm assuming that. And so this is, again, the limit as h approaches 0 of f of x plus h over f of x, all to the 1 over h power. So it's very similar, but instead of subtracting these things, we're dividing them. Instead of multiplying that by 1 over h, we're raising it to the power of 1 over h. And so this, as it turns out, if you do some mathematical manipulations, and Dr. Peyam does this in his product derivative video, if you do some mathematical manipulations, this turns out to be exactly equal to e to the power of the derivative of the natural logarithm of the function of f. And this is the logarithmic derivative, which if you study calculus, you know is equal to the derivative of f divided by f. So it's e to this power, which is pretty interesting. The thing is, that sort of is nice that it's true, is that if you do the product integral, which I'm notating as capital P of some function f, then it turns out that just as the product derivative is e to the derivative of the natural log of the function, then the product integral is e to the regular integral of the natural logarithm of the function. Now, this can get pretty hairy if f is not a nice function that goes with the natural logarithm, because the integrals of natural logarithms of functions can be pretty annoying unless it's like a particularly special case. So this is an interesting thing to consider and look at, and I think in this video I'm mainly going to just be looking at the product derivative, but I figured I would just show you both of them. So just to reiterate, the product derivative of a function turns out to be exactly equal to e to the derivative of the natural log of that function, and the product integral is e to the power of the regular integral of that function. So now that we've got those definitions down, I want to explore some interesting properties of this thing right here. So let's get to that. I also wanted to make a quick point before I continue that Dr. Peyam also explained that you can use differentials as a neat notation for product derivatives and product integrals. Product derivatives can be, instead of thought of in the usual Leibniz notation of the derivative of the function with respect to x, that this is the regular one, this is the regular plus derivative, the additive derivative, the one that we're all used to. I guess you could call it additive since we're talking about multiplicative. But in our sense, the multiplicative one is actually just df to the power of 1 over dx. And I think that's a really interesting notation, and it does make all the math work out brilliantly. It's really nice. Similarly, the regular integral is a sum over the function times the differential of x, whereas the product version is a product over the function to the power of the differential of x, and it makes all of the math work out brilliantly. It's such a neat idea to try and do a multiplicative integral, and I think it's such a I don't really have much of a concept of what it means really, of what exactly this entails. Like regular integrals are just the areas under curves, and regular derivatives is just the slope of a curve at a certain point, like the slope of the tangent line to a curve. But these two things, I'm not really sure like what it means, like in a physical sense. Like I don't really have much of a concept of that, and I would really love to learn more. So I hope Dr. Peyam does more of these things. I plan on reading up on them. But for now, in this video, we're just going to take a look at the multiplicative derivative, okay? Or the product derivative. So let's answer some questions there. So in my head, having taken a differential equations class, I thought, why not treat them like differential equations and see if I can find families of functions that are solutions to neat questions. And so, because there's differential equations, I thought we could call these productive equations. I think that's a cute little name. So let's say that. I think productive equations is a neat question. So productive equations, as I see them, are differential equations that also include product derivatives. So if a product derivative is involved in the equation of relating functions with functions as solutions, then it is a productive equation. Any differential equation that involves a product derivative or multiple orders of product derivatives is a productive equation. That's how I'm defining that. So let's get on with it. I mentioned order of derivative, right? Multiple derivatives. And so a natural question that arises is, what if I take the product derivative of a function n times? Right? What should that entail? Well, we know that, I'll put a question mark there because we don't know. Well, we know that the product derivative of a function is equal to e to the derivative of the natural logarithm of that function. Right? So if we want to find the second product derivative of this thing, we just need to plug this, we just need to take the product derivative of this thing. Well, the second product derivative of a function is therefore e to the natural logarithm of the original statement, this thing, right? E to the natural logarithm of e to the derivative of the natural logarithm of f and the derivative of that. So it's taking this thing and plugging it into the product derivative definition. So this is just taking the second product derivative. And what nicely happens is the natural logarithm of e to the thing, right? The natural logarithm and the exponent cancel, and we just get this back. And what we're going to end up with is just e to the derivative of the natural logarithm of f, and then we're taking the derivative of it again. And so, of course, this just turns out to be e to the second derivative of the natural logarithm of f. And I don't think it's hard to see that this is just going to continue, right? So I think it's pretty easy to see that the nth product derivative of a function is just e to the nth derivative of the natural logarithm of that function. And I think that's really neat. So it sort of carries over in the sense that this degree is going to sort of carry over into the regular derivative that we see in the power here, and I think that's pretty neat. But that's just sort of addressing a multiple product derivative kind of thing. Let's get to some productive equations. So in regular calculus, there's the question of, is there some function f prime, or some function that if you take the derivative of it, you get the function back? And that's a pretty natural question. So what you can do is you can divide both sides by f, and you get f prime over f, and this is just equal to the derivative of the natural logarithm of f. And because we divided that side by f, we get 1, right? And now to solve for the function, we have to integrate both sides. And we get that the natural logarithm of f is equal to x plus some constant, right? And then raising e to both sides, we get that the functions, the family of functions that are the solutions, are e to the x plus some constant. Well, this is equal to e to the x times e to the c, because that's how exponents work. And I will do a video on that eventually, really thoroughly explaining all of the rules and properties of exponents before we get to calculus. I just wanted to get this out first. And e to the c is just some constant, right? Because e is a number, it's about 2.71828, and raising it to a fixed power just gives another number. So this is some constant times e to the x, and those are the family of functions whose derivatives are themselves. So that's an interesting question. And of course the natural question arises, are there such functions when it comes to the product derivative? So let's take a look at that. So I'm asking now, if I take the product, if I take a product derivative of a function, can I get that function back? Right? So let's see. What is the definition of the product derivative? We have e to the f prime over f equals the function f. And so to get to the thing in the power, we just need to take the natural logarithm of both sides, and we get that f prime over f, which is again the derivative of the natural logarithm of f, is equal to the logarithm of f. But now to solve for f, we're going to do the same thing we did in the last problem, and we're going to divide both sides by this thing. So we end up with 1, because we're dividing by this, we get 1 is equal to the derivative of the natural logarithm of f over the natural logarithm of f. But this is now just the logarithmic derivative of the logarithm of f, which means this is the derivative of the natural logarithm of this function f that we don't know yet. And now to solve for f, we just need to integrate both sides, and I'm going to do this up here, right? We just need to integrate both sides, and we get that some x plus some constant is equal to the log of f. And now we just need to raise e to both sides to cancel once, and we have e to the x plus c is equal to the natural logarithm of f. And to get at f, we need to raise e to both sides one more time, and we get that f is equal to e to the x plus c. And again, e to the c is just some constant, so we can rewrite this as e to the c times e to the x. And this is the family of functions whose product derivative is the function. And it's pretty crazy, because what it is e to the power of the functions whose regular derivative are themselves, which is really neat. You don't really think about these things because product calculus is probably not a very common thing that people study, but I mean, come on, that's just lovely. A similar question would be, I think, a reasonable question, would be, are there any functions whose product derivative is the same as the regular derivative? Well, that's an interesting question. Let's explore that. So remember, recall the definition. We have that the product derivative of a function is e to the derivative of the function divided by the function itself, which is, of course, again, e to the natural logarithm of f, but the derivative of that, because this is the logarithmic derivative. And if you study calculus, you'll learn that, and it's not difficult. If you don't know it yet, that just means you don't know it, but it doesn't make it difficult, right? Always got to drink my trusty cup of joe. Seriously, my coffee is going to be the mascot of this channel. I'm going to make it happen. If you don't like it, you can off. Yeah, so this is equal to f prime, right? We're asking what functions have a product derivative that is equal to the regular derivative. Naturally, we have to take the natural logarithm of both sides, and if we take the natural logarithm of both sides, we just get the power back, and we get the natural logarithm of f, but primed, and we're taking the natural logarithm of that. So we get the natural logarithm of the quantity f prime. which means that functions whose product derivative is the same as their regular derivative are the functions where if you take the natural logarithm, if they are the functions that if you take the natural logarithm of the function and then its derivative, it's the same thing as if you take its derivative and then the natural logarithm of that. And I thought, what the heck? How am I supposed to solve this? Went to Wolfram Alpha, typed this in to solve for f, and it gave me a function back with like the exponential integral, which is not an elementary function by any means. And if that wasn't the worst part, it wasn't even an explicit solution. So it was like x plus a constant equals a bunch of stuff happening to f or y or whatever variable or whatever letter I used. But, you know, it's not only is it non-elementary, there's not even an explicit solution in terms of those non-elementary functions. So it's really just an awful problem to try and attack. But damn, is that a neat set of functions probably. Functions whose logarithm, the derivative of the logarithm is the same as the logarithm of its derivative. I think that's brilliant. I don't know how you would even like go about it, but it's pretty neat. So that's an interesting question. Another nice question would be, oops, I didn't mean to erase that. So what if we take the product derivative of a function and we get back e to the power of that function? I think that's a pretty neat question to ask. So again, this is e to the f prime over f equals e to the f, right? And because it's e raised to different powers but are equal, that means the powers must actually be the same, because if you take the natural logarithm of both sides, you're just going to get this back anyway. Equals f. And to solve this differential equation, we just need to divide by f. So we end up with df over f squared, we're taking the integral, is equal to the integral of dx, which is again x plus a constant. And this is just, what is this going to be? This is going to be negative f to the negative 1, right? So negative f to the negative 1 equals x plus a constant, which implies that f is equal to negative 1 over x plus a constant. Isn't that crazy? So just these simple reciprocal functions have the property that if you take their product derivative, you get e to the power of that function. I think that's really neat. Those are my explorations in what I like to call productive equations. Things that are differential equations but also involve product derivatives. Now, the next questions I wanted to answer were, are there any functions whose product derivatives are really, really neat? And Dr. Peyam did a couple of them. He did x to the x, which otherwise is really cumbersome in regular calculus, especially if you're taking the integral. But the integral of that is really nice. I thought if I remember correctly, it turned out to be like x times e or something, which is really nice. I thought it would be neat to try and put to the test functions like the gamma function and the Riemann zeta function. So let's see what happens there. So if we take the product derivative of the gamma function, we end up with e to the gamma prime over gamma, right? That's just a logarithmic derivative of the function. But this is a special function. This is the digamma function, right? It's specifically defined to be the logarithmic derivative of the gamma function, which, if you're not, sorry about this, the gamma function is a continuous analog of the factorial function, but it's x minus 1 factorial for integers, for positive integers x, then this relationship holds. For every other complex number other than negative integers, this is a completely valid continuous graph. It's defined by an integral. It's the integral from 0 to infinity of t to the x minus 1 times e to the negative t with respect to t. That's the definition of the gamma function. And this will give you the same values as the factorial function at positive integers x minus 1. So that's the definition of the gamma function, and its logarithmic derivative is defined to be this special function, the digamma function. And so the interesting question might be, what if we evaluate this function, this product derivative specifically at 1? Well, then we get e to the digamma of 1, and if you know anything about gamma functions or that particular field of number theory / complex analysis, then this is equal to e to the negative little gamma, which is the Euler-Mascheroni constant, or as Papa Flammy likes to call it, the Euler-Macaroni constant, which is of course the correct pronunciation. It does kind of look like oily macaroni, but so let's see. What is that number? So the gamma constant, little gamma, whereas this is capital gamma, this is lowercase gamma. It's defined to be the limit as n approaches infinity of, what is it? It's the limiting difference of the harmonic series and the natural logarithm. This diverges and so does this, but their difference converges to a value which is about 0.577, right? I think that's what it is. Yeah, it's around there, 0.577 or something like that. And it's very, very important in number theory, and analytic number theory in particular. No one knows if it's rational or not, but if it is, I think its exponent, I'm sorry, it's not its exponent. If this number is rational, it's been checked to so many digits that if it were rational, its denominator would have to be on the order of like 10 to the 242,000th power, which is absolutely bloody ridiculous. But amazing at the same time. So this is a really interesting number. It shows up a lot. It somehow has to do with products of primes, which is crazy. And I think that has to do with the reciprocal of this number, e to the positive gamma, which is just crazy. Because I'm pretty sure e to the gamma, so e to this number, not e to the negative gamma, but e to the positive gamma is equal to the product over the prime numbers, which is just wacky. A limiting product over the prime numbers. I just think that's so neat. But I just think that's really neat. You get the digamma function out of it just by taking the product derivative. One more thing I want to do is I want to take the product derivative of the Riemann zeta function because it's absolutely neat. So, the Riemann zeta function, usually denoted capital zeta of s, capital zeta of s, is when the real part of s is greater than 1, then this definition holds that I'm going to give you, and it's the sum from n equals 1 to infinity of 1 over n to the s, and what our amazing forefather of mathematics, Papa Euler, was able to show is that this is equal to a product over the primes of all things. So a product over all the prime numbers. I'm just using this fancy schmancy p to represent. It looks like the symbol for real numbers, but without the diagonal bar, so it's a p, and it's a product over the prime numbers. It is 1 minus p to the negative s, and p is just one of the, it starts at 2 and goes through the prime numbers, p to the negative s all to the negative 1. And this is a valid definition of the Riemann zeta function where s has a real part greater than 1. And what this allows us to do, because it's a product, is investigate its product derivative, which is really, really nice. So if we ask ourselves, what is the product derivative of the Riemann zeta function, then we can say that this is equal to e to the derivative of the natural logarithm of the Riemann zeta function. And now people have figured out what the derivative of the Riemann zeta function, or I'm sorry, the natural logarithm of the zeta function are in many different representations. There's a really, really neat integral representation of it using the prime counting function. But all I'm going to do is just take the natural logarithm of this product. So when we take the natural logarithm of so I don't want to have to keep writing e to the something every time, so what we're actually going to investigate is the natural logarithm of the product derivative, which means we're not going to investigate e to that thing, we're just going to investigate this power. Okay, so all I did was take the natural logarithm of both sides, so that we can just investigate the power. So we're going to take a look at the derivative of the natural logarithm of the gamma function. So the natural logarithm of the gamma, I keep saying, sorry, I'm just really excited because I love this stuff, and I'm a complete effing nerd. So the natural logarithm of the zeta function, we can do it with this product representation here, because the logarithm of products is really, really nice, because logarithms turn products into sums. So we can take the logarithm of this definition here, the log of the product over the primes of 1 minus p to the minus s to the negative 1. Negative 1 comes down, right? Part of the, so I should turn it into a sum first. So this is going to be equal to the sum over the primes of the natural logarithm of 1 minus p to the minus s to the negative 1, and given the rules of natural logarithms, we can bring the negative 1 down, and we get negative the sum over the primes of the natural logarithm of 1 minus p to the minus s. So this is just the natural logarithm of the Riemann zeta function, but remember, we're taking the derivative of this. So this whole time, all of these things have had the derivative taken of them. So what we can do with the derivative is derivative times a constant, derivative of a constant, the constant comes out. And the derivative over a sum is just the sum of the derivatives. So what I can do is rewrite this as the negative sum over the primes of the derivative of the natural logarithm of 1 minus p to the minus s. So we're taking the derivative of that and we're summing over those things, right? Oops, ooh, that was a horrible squeak. So we're just taking the derivative of that. And what we get is the derivative of the inside divided by the inside. So we get the derivative of 1 minus p to the negative s, and this is all with respect to s, by the way, divided by 1 minus p to the minus s. And the derivative of 1 minus p to the negative s is going to be the logarithm, so we have to multiply by negative 1, right? So the multiplying by the negative 1 here is going to cancel this negative 1 here. So we end up with, what we're going to get is log p, because it's the derivative, so the derivative with respect to the exponent means you have to take the logarithm of the base. And we have a negative here and a negative here that are going to cancel, so those go away. And then we multiply by the derivative of the power, which is just negative 1. So we end up with a negative 1 in the end anyway. But we still have to multiply by times p to the negative s. And this is all over 1 minus p to the negative s. And what I'm going to do now is I'm going to multiply the top and bottom by, well, first of all, I'm going to flip this difference because I'm just going to divide by negative 1. And so this is going to flip, and we're going to get p to the minus s minus 1. And now I'm going to multiply the top and bottom by p to the s. So we end up with the derivative of the natural logarithm of the Riemann zeta function is equal to the sum over the primes of the natural logarithm of p, and because I'm going to multiply the top and bottom by p to the s, this is going to go away, this is going to go away, and this is going to become p to the s. We get the sum over primes of log p over 1 minus p to the s. So this is the derivative of the natural logarithm of the Riemann zeta function. For the love of God, what a mouthful. But this is not what the product derivative of the Riemann zeta function is. This is the logarithm of the product derivative of the Riemann zeta function. So we need to raise this, we need to raise e to this power. But then look what happens when we do that. I'm going to erase all this intermediate stuff. So we're no longer taking the logarithm anymore. We are putting e back into it. And so raising e to this power gives us e to the sum over the primes of log p over 1 minus p to the s. But e to a sum of things is just a product of e to the power of all of those things. So this is the same as a product over the primes of e to the log p of 1 minus p to the s, but we can pull this out as a product, right? So we can, as a product of powers. So we can say that this is equal to the product over the primes of e to the log p all to the 1 over 1 minus p to the s power. And e to the log p is just p, right? Because the logarithm and the exponent cancel. And so we find out that the product derivative of the Riemann zeta function is equal to the product over the primes of p to the power of 1 minus p to the s. Which is just, like, what the heck? That's amazing. Like, what is that? So this is, p represents prime numbers, right? So what this is saying is that picking s, remember this is all for s with real part greater than 1. So picking some s value on that part of the complex plane, that means that this is equal to 2 to the power of 1 minus 2 to the s times 3 to the power of 1 over 1 minus 3 to the s times 5 to the power of 1 over 1 minus 5 to the s times etc., etc. A product over the prime numbers with these wacky powers, just strange powers, absolutely odd, just very, very strange. And this is the product derivative of the Riemann zeta function, and I find that absolutely just interesting, just so interesting. So sorry if that was rushed and maybe a little rambly. I have a feeling that the professor of mathematics that this is in response to will have no trouble following what I did here. I just kind of wanted to get this video out so that I could post it and have him see it, because I just love his channel, and I thought that I keep speaking of him in the third person because I don't know if he's going to watch this or not, but if you are, I really, really love your videos, Dr. Peyam. I think they're just fantastic. Please do more fractional derivatives and more product calculus. I think it's so interesting. I love calculus. It's my favorite part of mathematics, all the way up to complex analysis. And so, as you can see, I have a bit of a layman's understanding of how this stuff works. So I hope you enjoyed this, anyone that watches. And I just want to once again thank Dr. Peyam for putting up such interesting stuff. And again, congratulations on 25,000 plus subscribers. You deserve every one. Thanks for watching, and we will continue our exploration of trigonometry in the next video.